how we can perform text classification using global vectors. So we're going to use GloVe from Stanford with Keras to actually classify text from a Kaggle competition. Okay, so let's go ahead and see how we can do this. As you can see, the competition here is you can access this competition by clicking on this link, and we are predicting whether a given tweet is about a real disaster or not. So we're going to predict 1 if it's a disaster or 0 if it's not. So a simple binary classification problem. And the first things that we'll do is load the necessary libraries, and then let's load the train and test set, and let's check out our train set. We can see that we have the text and the target. We're not going to look at the keyword allocation, we're just going to use the text and the target from this. And of course we have the test set where we have the texts that we need to analyze. The first things that we will do is remove the HTML and URLs, and then remove the emojis and do a little bit of text cleaning, remove the punctuation as well, and we're going to use this this lambda function to do all of the above. Of course, these methods, you can find them in a different video in which I actually go through them in more depth. I'm going to put a link down below in the description for that video, and you can check that one out specifically to see how you can perform this text cleaning. For this reason, I'm not going to go into details here, but you can check out that video and see how you can perform this in more detail. Now we're going to remove the stop words. We're going to use an LTK for that, and the same, we're going to map this function to our text feature. And after we've done all this cleaning, let's see how our text feature looks like. You see now everything is lowercase, and we've done all of that cleaning, and it looks a lot better. As you can see, we have a much cleaner feature. Again, check out that video that I'm going to put a link down below in the description for, and see how you can perform text cleaning for these types of problems. Now let's go ahead and see exactly how we can use global vectors, GloVe, to perform these word embeddings. Let's see. Now you can find more details on how GloVe works on the stanford.edu website. Let's actually check this one out. And we can see that GloVe is an unsupervised learning algorithm that helps us obtain vector representations for words. In a previous video, we saw how we can do word embeddings for a baseline model, okay? But this way we can actually use GloVe. We can use pre-trained word vectors for this type of problem, because we will get a lot better results by using pre-trained word vectors. And because our problem is a Twitter problem, we can use this pre-trained word vector by accessing it at this link below. I'm not going to go into a lot of details when it comes to why we should use GloVe rather than, let's say, word2vec, okay? But a quick understanding of why would be that we can actually see that GloVe uses the frequency of co-occurrences rather than just relating their words to their context. So therefore, we have a little bit of more additional information with each of those words, okay? So GloVe builds these word embeddings in a way that a combination of word vectors relates directly to the probability of these words' co-occurrence in that specific corpus. So this is a very basic understanding of what GloVe is, but I definitely encourage you to check out their paper. Let's see where the paper is. It's actually here. So if we access this link above, you can read the paper that was written to explain global vectors in a more detailed manner. I definitely encourage you to go through this paper when you have more time, because it will clearly make sense to you after diving deeper into this problem. All right, but for this video I would like to actually see it in a practical way rather than just this theoretical way by reading the paper. Okay, now after we downloaded the Twitter data, again, you can download the Twitter data from here. It has 1.2 gig, so it's quite large, but nevertheless, this is the data that we're using. And you can see that we're using here, we're going to use the 100-dimensional data. So first, we need to create the corpus, and we're going to create the corpus using this method. So we're going to run this, and by creating the corpus, we can actually see that our corpus consists of 7,613 lists. So if we look at the corpus, we can see that the first element is a list of the words that are found in the first record. So this is what the corpus is. It's just a list of lists. Now we're going to split our data set in a train and test set, and we're going to use 0.2 for our test set. Therefore, we can run this, and now we have our train sentences and then train labels. Okay, let's actually check these ones out so we know what we're talking about. So our train sentences are these, and our train labels are these. So now we're going to use tokenizer, and then we're going to pad the sequences with a maximum length of 50. And we're going to use the actual number of words in our corpus, because our number of words is the length of the corpus, meaning 7,613. And we're going to fit the tokenizer on the train sentences. And now we can actually see the train sequences that are created from these sentences. Let's run this and then check them out. If we look at the train sequences, what we've done here, we've converted all of those words to their corresponding integers from our word index that is in the actual tokenizer. So, for example, 696 is mapped to a word that is found in our train sentences. So if we look at the train sentences, let's look at the first element. So reason is the second word, and it's mapped to 696. We will actually check our word index immediately, so you will actually see that reason is actually mapped to 696. But before that, let's just pad the sequences with a max length of 50. So if we pad them, if we check that one out, now we will see that in order for us to use it with Keras, we need to have this padded to a fixed length. So we're going to use 50 for a length, and each sentence will be truncated to fit in those 50 words. Okay? Of course, our tweets have less than 50 words, so therefore everything that is more will be added as a 0. So therefore that's why we have a whole bunch of zeros at the end, because we have all those sentences and then it adds zeros up until it fills that whole sequence of length 50. And we're going to do the same for the test sequences, but here, as you can see, we're not fitting the data because we already fitted on the train sentences. And now we're going to use the tokenizer to transform the text in the test sentences to our representations. So let's go ahead, we also pad them, and if we look at test, padded is the same, okay? It has the same length of 50, and it consists of those representations of those words. Let's actually print them out so we can see them again. We can see that we have these reason earthquake, and now we have these representations for those vectors. Okay, so we know that reason is 696 and deeds is 3739. So just to make sure that we understand where these numbers come from, we can check our word index. So we have 15,470 unique words, and if we check our word index, we can see that it's actually a dictionary in which the keys are the words that are found in that corpus, and then the values are just increments. It just assigns a number to each specific word in an increment of 1. So if we check the word index for the word reason, because it's a dictionary and we can access the key by just specifying reason, we can see that the number is 696. So hopefully now you understand how each word gets assigned to a specific value. It's based on the word index that is created by the tokenizer when you actually fit it on the text. Now let's go ahead and see another example. For example, for the test sequences, we have this representation, and if we print the specific record, let's see, listen should be 670, correct? So let's run this, and of course we get the representation for the word listen is 670. Now, we haven't done any proper embedding with GloVe, so let's actually show you how you can create the embedding dictionary using GloVe. Again, you have to download the Twitter pre-trained vectors. Again, I'm going to show you where you can download it from. Okay, so just go to nlp.stanford.edu/projects/GloVe and then download the Twitter pre-trained word vectors from here. And after you do that, you can use this cell here to embed it, to create an embedding dictionary that adds each vector to the word in the GloVe pre-trained vectors. So if we run this, it's going to take a little bit of time because there are a lot of words in this data set. And now if we check this dictionary, you can see what it did. It just added each word in this document. It mapped it to the specific vector. So you see that the word user is assigned this value, which is formed out of an array of 100 elements, because we are using the 100-dimensional word embeddings. And now we need to create the embedding matrix. So we're going to use the number of words, which is the length of the word index, plus 1, because we're going to have a for loop here. And we're going to create an embedding matrix, which is just an array of zeros. So for each word and its index in the word index, we're going to assign the vector that we see in here. Let me just print this again. We're going to assign this vector to the actual word in our corpus. So let's run this. Let's check the embedding matrix now. As you can see, it's an array of vectors, okay, of embedded vectors. And the position is the specific position of the word in the word index. So if we look at our word index, value for reason, it's 696. And if we get the element from the embedding dictionary, we can see that it's this array. And we can check that our embedding matrix at position 696 equals this specific array. and we can check and if it's correct, if it's true, and we can see that it's true. So therefore our embedding matrix was created correctly. So our embedding matrix is just an array in which we have each element of that array at the specific position corresponds to the word in the word index. So now we have the embedding matrix, and now we have the train padded and the train labels, and the test padded and the test labels. So these act as our train set and our test sets. So we have 6,090 records in our train set, and we have 1,523 items in our test set. And as you can see here, we have 50. So we have 50 features because we have vectors of the length 50. So our baseline model with global vectors will be the same model that we used in a previous video when we've done text classification with Keras. And I'm going to put down a link in the description to that video so you can see the results from that specific procedure compared to what we get with global vectors. And we can run this. But before I start, I just want to thank you for subscribing to our channel and for liking this video, because we really want to help you guys grow, and hopefully this video will help you in your machine learning journey. So let's go ahead. As you can see, what we've done here, we created the embedding layer and we initialized it with our embedding matrix. Okay, it's not trainable because the word vectors are already trained, and we have the input length of max length, which is 50, and this is our corpus, okay, the number of words. Just to understand how this differs from the previous model in which we didn't use GloVe, let's actually check that one out, and we can see that our embedding layer, of course, had our corpus, and it had 32 dimensions with the max length of 50. Okay, so we're not using here, as you can see, we're not using our embedding matrix. So this is the difference between using GloVe versus just using a normal embedding layer, because our embedding matrix adds more information that we can use to get better results for text classification. So let's run this, and we're going to fit this model on the train set. So we have the train padded and the train labels. We're going to run it for 20 epochs, and our validation data is our test set. Okay, we have test padded and test labels, as we've seen earlier. If we look at the previous model, we can see that we had the same 20 epochs and the same data. Okay, we had the same train set and test set. And if we run this, let's see what we get. Let's wait a little bit of time. Now that our model finished training, we can see that our validation accuracy is 0.77 and our accuracy is 0.88, compared to our previous model that had the validation accuracy of 0.74. So we can see that our model is better than with GloVe than without it. So now let's predict our actual test set, because now we've trained our model and we've seen the validation accuracy as well. So we're going to use the tokenizer and we're going to transform those text to sequences as we did before, and then we're going to pad them using, of course, 50 as the length, and then now we're going to predict on the padded, and we're going to transform them to integers. Okay, so if we check the predictions, we can see that it's an array, okay, of the actual predictions that are from 0 to 1. And if we check the integers, then of course we have just zeros and ones. If we check padded, the fifth element, As you can see here, we have an element that only consists of one word. This is quite interesting. Let's see what this word is. First, let's predict to see the actual prediction, and it's 0.92, so it's pretty. So our model is actually convinced that this is a disaster, even though our sentence is formed out of just one word that was recognized from our train set. Let's actually see what this word is. And for that, we can check the inverse. And we're going to use this decode method. And if we decode the sequence, we can see that the word that was taken into consideration was earthquake. So our model predicted, even for this small example where you only have one word, it managed to find its meaning, because earthquake is a disaster. So even though all the other words in that sentence weren't necessarily found in our train set, it still managed to perform very nicely, and we got a pretty good accuracy of 0.92. Okay, so this is to show you how good Global Vectors is for text classification. I really hope that you enjoyed this tutorial, and I'll see you in the next video.